We talked about Taylor series in class, but there's an important concept called interval of convergence that I wanted to talk about here a little bit. This is the Maclaurin series for e to the x, this guy right here. And a Maclaurin series is just a Taylor series that's centered at x equals 0. And this looks like this. And then there were three others that were pretty important that we talked about. There's the Maclaurin series for sine of x, and it looks like this guy right here, these odd powers of x, alternating positive, negative, and then having that factorial down in the bottom like like all Taylor series do. I guess not all of them. Sometimes they get canceled out, as we'll see. And here's the Maclaurin series for cosine of x. It's really similar to sine of x, except now we have even powers of x. And so these polynomials are going to not only estimate, but they equal the value of each of these functions for any x, these infinite series. One last one I want to look at is 1 over 1 minus x. This Maclaurin series has the awesome power of just being the sum of powers of x, and that's a really clean series. So these are all important Maclaurin series. I mentioned in class that each of these series had a radius of convergence, and for the top three, the radius of convergence, which we'll call big R, is actually infinity. These series work for any x. So it doesn't just have to be, even though this series was generated with x right around x equals 0, these series work for any x. This infinite series will give you the value of this function for any x. But this guy was different. This one had a radius of convergence of just 1. So, and what that means is that it was centered at 0, so it worked for all the x values to positive 1 and all the x values to negative 1. So in between those 2 points. And I want to talk a little bit about why. Okay, here is the series f of x, not the series, the function f of x equals 1 over 1 minus x just graphed. And this is the function that we're trying to estimate with this Maclaurin series. And here I just have, this is actually a Maclaurin polynomial. It's not a series yet because I have a fixed number k. I'm just going to go up to 10. But as I play, higher and higher orders of Maclaurin series, you'll see how they best fit. Let's just go up to the first degree Maclaurin series. Will look like this. This is just where the first derivatives match. This is where the second derivatives match. And this is where we have a degree 3 polynomial. So everything up to the third degree, or the third derivative, is going to match. And you can see how this red Maclaurin series or polynomial is getting closer and closer to 1 over 1 minus x, but not so much over here, like just as we're centered at x equals 0. And it's getting closer. If I take the fifth power, it gets pretty close. And sixth power, seventh power, eighth power, ninth power, it's getting super close. There's a 10th power Maclaurin polynomial that's trying to estimate 1 over 1 minus x. So let's take this up to, we could take it up to 50 or whatever we want. And you can see how that's even all those high powers, it's getting closer and closer, and yet it's still struggling really to get past the negative 1 to 1 bound. And so we could go up as high as we wanted to, but this Maclaurin series is just never going to be a good estimate for anywhere on 1 over 1 minus x except for the negative 1 to 1. It's getting closer and closer, but there's a point at which it's just no good after that point. So I want to explore sort of algebraically why that happens. Okay, we want to show why the interval of convergence for the Maclaurin series of 1 over x minus 1 is this. Why is it bounded in that way? And the way we're going to do this is by using the ratio test. So we'll use the ratio test for convergence of a series. And so we have to ask the question, for which x does this series converge? So this is something slightly new. When we were looking at series before and invoking the ratio test, we didn't have any x's in here, but this is a totally valid question. We can say, okay, does it work for when x equals 3? Does it work when x equals 0.5? Does it work when x equals negative 7? And so we're going to look at the ratio test and find out for which x's will this converge. And so the ratio test asks us to look at 2 successive terms of the sequence and what the limit is of the ratio of those terms. So we're going to look at the limit as n goes to infinity we need the n plus 1th term of this over the nth term and the absolute value of that. So we need the n plus 1th term over the nth term. And we're going to see what this, will it converge, will it diverge? You remember the ratio test, when you look at this, if you get like the limit is less than 1, then it's going to converge. If the limit is greater than 1, then it diverges. And if the limit equals 1, the test is inconclusive. So we're going to examine this and just kind of see what we see as we go along. So this will definitely equal the limit as n goes to infinity. Let's see, x to the n plus 1 over x to the n is just plain old x, because you've taken n powers out of here and canceled them with this, so you're just left with an x on top. This is, this is not dependent at all on n going to infinity. This is just the limit of some x, and so this is just equal to the absolute value of x. The ratio test says that if your limit is less than 1, you will converge. So if x, so we now know that if x is less than 1, the series converges. And if the absolute value of x is greater than 1, then the series will diverge. This is just from the results of the ratio test. For when our absolute value of x equals 1, this test is inconclusive, so we need to look at those cases separately. So those are two special cases. So say that x equaled 1, then our series would be, looking at this series right here, it would just be, this would be a 1 right here for x, and so we would have 1 to the n. This is just 1 plus 1 plus 1. This is definitely a divergent series. And then if x equaled -1, we would have -1 to the n, and this is 1 minus 1 plus 1 minus 1 plus 1. This doesn't go off to infinity, but it doesn't converge, so it is also divergent. So we use the ratio test to identify that for these values, it definitely converges. The series converges. We had to go separately and test these two endpoints. At this point, we weren't really using the ratio test. We're just looking at two very special cases where x equals 1 and x equals -1 to determine, what would those series look like, and could we tell if they converged or diverged. They were both obviously divergent. So the only time that this series converges is at these points right here. So the series x to the n from n equals 0 to infinity converges for x, absolute value of x is less than 1. This is why we say that the radius of convergence for this Maclaurin series is absolute value of x less than 1. This last example is to show the interval of convergence for sine of x. We already know that it's infinity, but we want to show why the interval of convergence is, that it works for all real numbers. So show that for this Maclaurin series, the interval of convergence is infinity. This would be a really good one for you to do on your own, just for the practice of seeing if you could justify this. And so go ahead and pause the video and try to show this using the ratio test that this interval of convergence would be infinity. Okay, hopefully you've taken a stab at this one. And here we're going to use the ratio test again. And we're going to look at the limit as n goes to infinity. This time, the terms we have to be really careful of. So we're interested in we're talking about absolute value, so we don't even really need to consider this guy. So as we look at this, we need to keep track of what term we're looking at. In the numerator of the ratio test, we need to go one more term. We need to let n equal, and we need to look at the n plus 1 term, and here we look at the nth term. So here the n plus 1 term, and here the nth term. So just be really careful as you're counting these that you're looking truly at letting n be n plus 1. So this would be x to the 2 n plus 1 over 2 to the n plus 1 factorial. So again, in the numerator, we need to be looking at the n plus 1 term, so that is going to go in for n. The bottom is just regular old x to the 2n plus 1 over 2n plus 1 factorial. And we can simplify this, and we're a little bit careful as we're simplifying. So in the numerator, we have x to the 2n plus 3 over 2n plus 3 factorial. And in the denominator, we still have x to the 2n plus 1 over 2n plus 1 factorial. Things will cancel, so we have the limit as n goes to infinity. It looks like we have 2 more powers of x than we do in the denominator, so that will be x squared. And then in the numerator, we're going to have a lot of these guys will cancel. This whole thing goes away, and we're left with just 2n plus 3 times 2n plus 2. So 2n plus 3 times 2n plus 2. So make sure and convince yourself that you believe that this is the result of simplifying. And then we have to think of what happens to this expression as n goes off to infinity. Thinking that x is a fixed number, which it is for our purposes here, n is the guy that's moving, and as n gets bigger and bigger and bigger and bigger, this whole expression is going to go off to 0. This equals 0. This is less than 1. So for the ratio test, this is good news. That means that the series converges for all x. This series right here will converge no matter what x is.